Many of the examples we do for resonance structures are going to be very symmetric molecules, where it's pretty clear to us that the different resonance structures are all going to look pretty much the same. And so we can say that it's going to have a uniform amount of time in each of the forms we can draw. Try sketching out ozone, O3, or the carbonate ion, CO3 double minus, as an example of that. Now, what happens when you don't have that kind of symmetry? Well, you're actually going to have to think through it pretty carefully to think about which one's going to be the most stable. Now, we could go to the supercomputing cluster and upload it and run the simulation for a couple of days or weeks and get a good quality answer out of that that tells us how energetically favorable each of the forms are and the kinetics of interchangement. And at that point, we can finally come up with an argument. Or we can do it like this. We're going to draw out our resonance structures, and we're going to decide which one it's going to spend the most time looking like it based on these rules. So small formal charges are going to be more stable than large ones. In other words, if I've got an atom and another atom and another atom, and I've got a +2 and a -2, why? Shouldn't this just duck in and turn it into a triple bond and get rid of the charge on both of them? That's what we're going to see happen. We should see those just cancel out, and we should have things focus on small formal charges. Those are going to be much more stable than large ones. Also, if we have a really electronegative atom, that's the one that should be getting the negative charge. That's the one that's really good at grabbing the electrons in the first place. So if I've got a fluorine and a carbon and some other stuff, and I'm not going to specify the rest of this molecule. I'll just go ahead and put some extra stuff on this one. If I have to put a minus sign on it, that minus sign belongs over here on fluorine because it's the one that's really electronegative. If I've got a minus sign sitting on carbon, right there next to the fluorine, how's that work, right? This thing is so phenomenal at grabbing electrons. Carbon's not keeping an extra bowl of chips at the party. It's got a really hungry hippo over here wanting to grab the bowl of chips, to use a really tortured analogy. That's what we're going to be talking about for where the electron belongs in terms of electronegativity. Now, here's what I'd like you to do. Go ahead and pause and try drawing some resonance structures for this molecule, and we'll decide which one is the most stable. I'll mention that we're implying the order of the molecule, so it's a nitrogen atom, a carbon atom, and an oxygen atom. And we're going to set up bonds and come up with charges. So go ahead, pause the video, and give that a try. Okay, now what I need to do is I need to figure out how many electrons I've got to work with. Nitrogen has 5 octet electrons. Carbon has 4 octet electrons. Oxygen's got 6 of its octet electrons, and the minus charge gives us an additional one. So I'm at 9 plus 6 is 15, plus the charge gives me 16 electrons to work with. So I've used 2, 4, 6, 8, 10, 12, 14, and 16 electrons. Now I've got to start shifting electrons around because carbon is nowhere near its octet. So one possibility would be to have an oxygen pair donated and a nitrogen pair donated. I'm going to leave this skeleton structure here as a starting point, and I'm just going to draw some of these so that I can save myself some time in the coming ones. So I said I'm going to turn one of those oxygen pairs into a double bond, one nitrogen pair to a double bond. I'm going to have this and this. Carbon's now up to its octet. Nitrogen is at its octet. That's drawn better. I still have oxygen over here, and I didn't draw in its 2 remaining electrons. Remember, I used electron pairs. I used this pair to make a double bond. These 2 pairs were untouched. So now let's think about our formal charges a little bit. We see that we still have the same number of electrons. If you want to pause and count them, go ahead. But now we can go ahead and figure out our formal charges. Nitrogen brought 5 electrons to the party. It currently owns 2, 4, 6 total electrons. So 5 minus 6 gives me a -1 charge on nitrogen. Carbon, it brought 4 electrons. It currently has access to 1, 2, 3, 4. So formal charge will be 0. Oxygen brought 6 electrons. 1, 2, 3, 4, 5, 6. 6 minus 6 gives me another formal charge of 0. So my minus 1 charge, notice when we add up all of these, I get the same charge that I should have. That's good. Means that I didn't screw things up. If it doesn't match, there's an error. So that's how these charges are going to look. But which electron is the most electronegative? Which atom is the most electronegative? Oxygen. So what's my minus sign doing over here on nitrogen? That's not likely to last very long. It's going to resonate to a different form. Now let's try a different form. Let's try just having oxygen kick in a double bond, and maybe let's have oxygen make a triple bond. Let's do carbon triple bonded to oxygen. I would use 2 pairs up to make that triple bond. This one would be untouched. Now I'm still going to have my other direction sitting still and doing its own thing. Now let's check my octets. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. All of the atoms are at their octets. Nitrogen brought 5 electrons. It currently has 1, and then these 6, so a total of 7 electrons. Boy, if we thought it was bad before, it's even worse now. It's going to be at a minus 2 formal charge because it brought 5 and now it has 7. Carbon brought 4. It's got 1, 2, 3, 4. Carbon remains at 0. Oxygen, it brought 6. It has 2, 3, 4, 5. It's at a plus 1. Our most electronegative atom now has a positive charge. And we haven't made our formal charge as small as possible. This one's going to be terrible. So let's try doing it the other way. Let's try getting a triple bond over here by nitrogen. We'll have our carbon, we'll have our oxygen, single bond. So the oxygen is still going to be the same as it was right up here. Carbon's at its octet. Nitrogen, we took this pair in and this pair in. Or I guess I should point up at this structure. I'll still have 1 pair left alone. Now let's check our formal charges. Nitrogen brought 5. It has 2, 3, 4, 5. Its charge is going to be 0. Carbon brought 4. It has 1, 2, 3, 4. Its charge will also be 0. Oxygen brought 6. It has 2, 4, 6, 7. Oxygen is going to be at a minus 1. Notice in all 3 of these examples, like I pointed out before, we still total up to our minus 1 overall charge, which means that they are all self-consistent. This one is terrible because it breaks 2 rules. This one's not great because it breaks 1 rule. This one is the best because it fills all of our rules. Small formal charges, they've been minimized, that's a good thing. And our negative charge is now on the most electronegative atom, oxygen. So that would be the form that I expected to spend the most time in. Now again, how do I know how much time it's spending in each of those? Complicated methods that are not appropriate for Chem 1. But if I just was going to make up some numbers that seemed realistic to me, I'd probably say it's spending like 85% of the time in this form, maybe 10% of the time in that form, maybe 5% of the time, other way around, maybe 10% in this one over here, since we said it's not totally terrible, and this one maybe 5% of the time or less. I completely made up those numbers. I wouldn't be shocked if you went to a computer and you found out it's spending 99% of the time in this form and minimal amounts in either of the others. That wouldn't shock me. But I don't care. I'm not asking you a question like that ever. I'm just making up some numbers to give you some idea of what we're talking about. We can come up with an intuitive level understanding of which one is favored. That's how we do it.